All right, so the title is, as you can see, Stochastic Inference with Deterministic Spiking Neurons. I chose this title because this is the title of our first paper on the subject, but if I wanted to be terse, I would say, just by using a couple of key words, it would be probabilistic computing with spikes. So if I were to show you this movie and ask you what you think this represents, it probably depends a little bit on your training, what you're going to see. So if you're coming more from the direction of neuroscience, you are, I would say, more likely to see something like a spike activity pattern with maybe some individual neurons starting to fire and to burst. If you come more from the direction of physics, in particular solid-state physics, you might tend to see a slice, a microscopic slice through a ferromagnet. And this is indeed the well-known Ising model with the Hamiltonian. It gives you the energy of the system that depends on the interaction between the electrons that generate the magnetic field and some external field. The key idea here is that the ensemble dynamics are so-called Glauber dynamics. So essentially the system, the state of the system jumps through the energy landscape or the associated probability landscape and essentially samples from the underlying probability distribution that is given here. So I'm going to argue that under certain assumptions and with a certain kind of architecture, spiking neural networks essentially do the exact same thing. So obviously this is about Bayesian inference, and I don't need to discuss to motivate this idea much, I guess. So we have an increasing amount of experimental results that confirm or at least lend support to the idea that the brain does some sort of Bayesian information processing. You have these very old results over here from psychophysics and some more recent results where these guys over here have shown that ferrets build something like a Bayesian base optimal internal model of their surrounding. And then I like the example from yesterday very well with the cow. So I Googled a little bit and I found something similar. This is a little bit easier to see because humans are pretty good at recognizing faces. For those of you who still don't see the character in the picture, I've added a reference over here. So the idea here is that additional knowledge or evidence about the things that you see change your posterior probability of what you are actually seeing. So why do this with spikes? Well, on one hand, of course, you are trying to understand biology. And on the other hand, even if you don't care about biology, if you implement Bayesian inference in spiking neural networks, you're going to be able to exploit all of the efficient neuromorphic hardware that we heard about. So you're going to be able to do this with a very low power consumption or a very high speed or whatever other advantages you have. But maybe more importantly, and I'll try to argue this toward the end of my talk, you also actually gain a computational advantage over non-spiking models. So going back to this idea of sampling, this is what sampling represents. In this particular case, Gibbs sampling, you have a system and the state of the system travels through a probability landscape. And by gathering samples, this system approximates some underlying probability distribution with an increasing degree of accuracy. Of course, the first question is, how do you interpret spikes in this framework? What is the x and the y-axis? And this interpretation goes back to work from Wolfgang Maas' lab, and the interpretation is the following. Whenever a neuron spikes, a neuron represents a binary variable. Whenever it spikes, it switches from a 0 state to a 1 state. Now, and stays there for a certain duration. Details don't matter. In our particular case, it's the refractory period of the neurons, but this can be softened. So in order to be able to sample from this probability distribution, neurons need to interact, and this is what the interaction needs to look like. So this is the membrane potential of the neuron, and it turns out that if you plug in the Boltzmann distribution into this equation, then the membrane potential of the neuron looks exactly like you would expect it to look. So you have some offset plus the sum of PSPs from other neurons. If you play a bit around with this equation, you get an activation function of a neuron that has this shape. This is a logistic function. And again, we know this from Gibbs sampling and from various other models. So you might tend to say, well, okay, this is easy to do with spikes. It turns out, actually, that it is not so easy to get a logistic function or a symmetric activation function from LIF neurons. So you know that LIF neurons are a type 1 model or something similar. So the activation function isn't drawn here, but basically, if you inject a constant current, the firing rate will be 0 and to reach the Rio base, and then it will go slowly up. This is, of course, a non-symmetric function. By adding noise, and you do need noise for the stochastic computation, you still get a strongly asymmetric function, something like this, this black curve over here. So we try to find out why this happens. Now, there is some theory, there are several theories actually that describe the activation function of LIF neurons. It turns out, though, that they work only in the more extreme cases, where the synaptic time constant is either much smaller than the membrane time constant, or it is much larger than the membrane time constant. And in particular, we are interested in the case where the refractory period of the neuron is in the same order of magnitude as the synaptic time constant, because this is the representation of the binary 1 state of the associated random variable. So we need to actually, we need to come up with a new theory, because the existing theories, that's the black curve and the blue curve, do not fit the simulations very well in the regime that we care about, which are these green crosses over here. So we need to come up with an entirely new theory. Please do not read these equations. I just want to show them to show that they exist. They look complicated. They're actually rather easy to compute, because they only include, they only require the computation of Gaussians and error functions. So while trying to get this probabilistic inference done with, I would say, more biological models of spiking neurons, we came up with a theory that works, a theory of predicting the activation function of neurons that works in any regime, and in particular in the regime that we care about, because if you play around with these equations, you're going to see that this term over here is the one that allows neurons to have a more symmetric activation function, and this term over here has something to do with the effective membrane time constant. It needs to be small, and this you can reach in the so-called biological high conductance state. So this would be a nice, an interesting hint of why neurons in the brain might be in the high conductance state. So with this theory now, it's rather straightforward to implement, design networks that sample from arbitrary distributions. In this particular case, it's a Boltzmann distribution. You can see that this works nicely. So the sample distribution in blue is very close to the target distribution in red. And now I can do, if you have a sampling network, it's almost immediate to actually do inference by clamping individual neurons. This would be providing evidence to the network. So this would be a simple example of a network that we train to recognize 3 digits. It's a very small network, just about a bit more than 100 neurons. And by clamping a couple of pixels in the middle of the image, the network stops sampling from the entire probability space and rather samples only from the states or the digits that are actually compatible with the evidence. So this is a very simple example of inference. I don't have time to go much into this, but there is a critical question: where does this noise, where does the noise come from that you require to make these networks stochastic? This is indeed an important question for a hardware implementation, because getting good noise is not that trivial. It turns out, though, that you can get excellent noise from random networks that have inhibition as well. So this would be an example over here where you decrease the size of the background network that provides the noise. If you do this with Poisson sources, as you would do it if you have an arbitrary amount of sources, as you do in software, you see that the performance becomes worse, but with the balanced background network, you see that the performance of the network does not decrease significantly. So this is just in passing. Now, the fact that we can do this with a LIF network allows a straightforward implementation in neuromorphic hardware, and this would be one of our chips. You heard about this yesterday, I think, in Karl-Heinz's talk, and Johannes might be talking more about this later. This is just a simple network that samples from a distribution over 3 random variables. And it does this pretty well. Now, the key aspect here is that it does it extremely quickly, since our hardware is 10,000 times faster than its biological archetype. So if you would run this simulation, it's about 100 seconds of biological time. In a software simulator, it would be done in 10 seconds. If you do it on the hardware, it happens in 10 milliseconds. So basically, you press the enter button and you get the results immediately. As a final point now, of course, you can make these networks more complex and do the whole deep learning stuff that everybody's doing nowadays. So you generate these hierarchical LF networks, which are equivalent to deep Boltzmann machines. And it turns out that these are pretty good. So if you use very simple training algorithms, such as contrastive divergence and something called coupled adaptive tempering, then you get an accuracy of about 97% on the MNIST data set. And this is only slightly worse than an equivalent Boltzmann machine trained with the exact same algorithms. The Boltzmann machine does 97.1% or so. Now, what you see here is an LIF network dreaming. So you don't present it with any evidence. It just dreams about the digits it has learned. Actually, it turns out that this is really hard to do with classical Boltzmann machines. This would be another example where classical Boltzmann machines use Gibbs sampling. So these would be the modes that the classical Boltzmann machine touches, or the digits that it dreams of. And you see that it stays in a single mode, so it doesn't mix between the digits. So this would be a very bad generative model, whereas the LIF network mixes pretty well. And the reason why it's able to do this, so mixing means being able to overcome energy barriers to switch between energy minima. The reason it can do this is that we can implement spike-based short-term plasticity into the synapses. So whenever an ensemble of neurons a sub-ensemble of neurons that encodes, say, the digit 3 starts spiking, synapses are going to be first strengthened, and then the image becomes sharper, and then the synapses are going to be weakened. So essentially, the energy well in which the system sits is going to go up and is going to catapult the system out of its current state, thereby allowing much better mixing. So this would be an example of what Gibbs sampling would do versus LIF networks. So here's the classical Boltzmann machine sampling from 7s. And here's the LIF network sampling basically from the entire landscape of digits that it has learned. So I would argue that this would be a key advantage of spiking networks versus classical non-spiking networks. So as a summary, I will not go through all of this again, but maybe just one short take-home message is that if you work like this at the interface between biology, hardware, machine learning, and theory, I hope that I was able to argue that you can learn a lot about all of these individual fields. Thank you.